Hello everyone, I am Zhan Xiangsong from Huazhong University of Science and Technology. This is a joint work with professors at University of Indiana University Bloomington and Nankai University. Today, with the popularity of the Internet of Things, there is growing demand for effectively connecting IoT devices and users. Lots of messaging protocols are proposed to meet this demand. According to the top communication protocols from Eclipse IoT Developer Survey and the results of 4 commonly used messaging protocols on Google Trends, our research subject MQTT has become arguably the most widely adopted for IoT in the world, due to its lightweight and efficient features. So how MQTT works? MQTT uses a publish-subscribe pattern to decouple the client that sends the message from the client that receives the message, by allowing them to communicate without having direct connections or knowledge of each other's existence. The essence of this pattern is that a middleman rail called a broker is responsible for routing and distributing all messages. Publishers send a message with a topic to the broker, and subscribers subscribe to the topic from the broker to receive message of interest. However, is this decoupled method of message transmission pattern truly secure? Especially considering that there are over 70 open source implementations at GitHub, each with its own heterogeneous MQTT implementation. One of the most popular brokers is Mosquitto, with more than 800,000 deployments according to the data gathered from ZoomEye, the cyberspace search engine. However, little work has been done to verify the security of MQTT implementations, especially for the delivery of messages. So, as a messaging protocol, there are numerous messaging flows specified in the MQTT specification. For example, the IoT device can initiate a connection to the MQTT broker by sending a connect package with a where message. As the specification states, the where message must be published after the network connection is subsequently closed. Except for those predefined messaging flows in the specification, customized messaging flows are often tailored to specific business requirements or application scenarios in implementations. For example, QoS2 offers the highest level quality of service in MQTT, ensuring that each message is delivered exactly once to the receivers. As shown in the figure, Mosquitto stores unfinished QoS2 messages in an in-flight queue. After the in-flight queue is full, the new valid QoS2 messages will be cached in a cache queue. Thus, the messages in the cache queue will not be delivered until there is a vacancy in the in-flight queue. Additionally, we found that the implementation of the authorization mechanism is also diverse, even though most of the brokers we analyzed exhibited a relatively consistent authorization model, which can be modeled as a 3-tuple client, topic, and write, to indicate that the subject client is authorized to access the object topic with an access right. However, due to the protocol's flexibility in the authorization mechanism, when and how permission checks are executed is entirely up to the developer. This could lead to incorrectly implementing authorization checks, and such customized messaging flows and authorization mechanisms in open source implementations lead to many authorization-related logic flaws. However, there are no comprehensive methods to analyze the security of messaging flows of open source MQTT brokers. Here is a motivating example about logic flaws in Mosquitto. As shown in the figure, the malicious user first publishes a QoS2 message to the broker, and Mosquito chooses to store the message and await the publisher's publish release package for delivering the QS2 message to subscribers. Despite the permission revoke action 2 marked in red, the malicious user is still be able to send the instruction like open the door, open the lock to the device through the delay-triggered QS2 message in step 4. This is because Mosquito lacks permission check for the sender of the publish release package. In our analysis, we focus on IoT systems that use MQTT brokers to manage and mediate communication between clients, including users and IoT devices. The administrator can grant other users access rights for IoT devices. The malicious user can collect and analyze network traffic between the broker and their own clients, but cannot eavesdrop on or interfere with communication between other users and the broker. We consider the situation of device sharing, which has become pervasive today in places like hotels, Airbnb, apartments, and other vacation rental homes. In these scenarios, users' access rights are subject to revocation and expiration. Next, we will detail our method for analyzing open-source MQTT implementations. Specifically, we propose a specification-driven and static analysis-based approach to model and verify messaging flows in open-source MQTT broker implementations. In simple terms, we use the MQTT specification to guide us in identifying key state transitions in MQTT implementations. Then, we created an abstract implementation-specific model. Finally, we applied the model checking tool Spin to verify safety properties on the model. Firstly, we proposed the general definition of an MQTT broker model, which we described using a state machine. Here, V is a finite set of whose value collectively constitute the states of the MQTT broker. Specifically, we extracted this information from the MQTT specification. For example, the specification states the session state in the server consists of the client's subscriptions. Like this, we have fully analyzed the entire protocol specification and constructed the following table containing all state variables. Moreover, in the model definition, O is a set of generalized low-level operation on the variables in the set V, and S is a set of states. A is the client actions, and delta is a transition function that drives the system transition from one state to the next. And SP is the security properties to be verified. Next, we will detail how to construct a state transition model from source code for each MQTT broker based on model definition. In the first step, we apply the off-the-shelf static analysis tool SVF to help identify key basic blocks in the code. A key basic block is a basic block in the broker's CFG that performs at least one operation on a state variable. Specifically, we first mapped the state variables to the corresponding variables in the source code manually. Then, we used pointer analysis to locate all the places where the state variables are accessed or modified. We recorded this information and marked the relevant basic blocks as key basic blocks. For example, the second line of the code is a read operation on the state variable where message, and the third line is a remove operation. The next step is to extract the execution order of these blocks in the control flow, which is also defined as path types. Pass type is a unique sequence of key basic blocks and represents the processing logic semantics of an MQTT packet in the implementation. We also record permission-related constraints along pass types. Finally, since there are many mutually exclusive conditions on the pass types we extracted, just like the figure on the right, the conditions for variable A on the pass cannot be satisfied simultaneously. So we use a simple execution tool Haybear to serve pass conditions and exclude false pass types, thus obtaining effective pass types. Here is a complete workflow of modeling MQTT implementations. We converted the source code of the implementation into vim-ir as input and use static code analysis to identify key basic blocks and extract all effective pass types from the control flow graph. We completed this process separately for different MQTT actions or packets, like publish and subscribe. Consequently, we currently get the handle logic of each MQTT action or packet in the implementation. Then we translate the pass types into the programming and modeling language for model checking. Note that each MQTT action has multiple different pass types and corresponding handling logic. Therefore, we create a transition function for each pass type, which drives the state transition of the entire model. The model checker then helps us explore all possible states and checks if these states violate security properties defined in the model definition. For example, a property can be when a message is accepted and delivered by the broker, the sender of the message should have the right to send that message. Okay, let's look at an example that violates the property. This is one of the authorization-related logic flaws identified in FlashMQ. Specifically, a malicious user, as a hotel or Airbnb guest, can take control of any device that does not belong to him by creating a weird message with device-specific topic. The underlying reason is that the broker neither checks the permission when accepting the weird message nor when delivering. Okay, now its findings. By applying the tool to 7 open source implementations, we uncovered 7 types of zero-day authorization-related logic flaws. And the MQTT brokers of major IoT service providers like AWS, IBM are also susceptible to the flaws we have identified. Okay, that's all. Thank you.